Okay. Okay. Got a few people joining in here. Wait a few moments. Okay, just kind of waiting for the little ringer here to stop ringing. Okay. Everybody have a nice Turkey Day?
I did.
Good. So this is our last week of lecture, if I remember right. Tonight and Thursday are the last lectures for this course. I want to thank everybody for being patient and working with me and the school with this whole COVID virtual thing. I'm sure it's been challenging for everybody. But as we draw near to the end here, my plan is we had not quite finished our lecture from last time about how to use the energy methods. So I have the rest of that lecture, which basically goes through an example of finding a deflection for a truss. And then I have one more complete lecture set up to deal with column buckling. So I thought what we would do is, since we have basically about 1.5 lectures left to cover all the material that we had hoped to cover on the syllabus, I think what we'll do is tonight we're just going to finish up the lecture on energy. So we can kind of take our time, finish that up. That's not going to take too much time. And then we can talk about the final. I think that'd be a good use of our time tonight, is to finish up the lecture and then dedicate whatever time you guys want to spend on asking questions, or if you have questions about the final, which is a week from today at 5 o'clock. Okay, so it's not 5:30, it's 5 o'clock, 5 to 6:50, 1 week from today. And then on Thursday, we'll do the last lecture on column buckling. How does that sound for everybody?
Good.
All right, got one good.
Sounds good to me.
Okie doke. All right, I think we got most people here now. Okay, so why don't we finish up our last lecture on energy methods? If you recall, I know this was before the cranberry sauce, so things are a little foggy, but if you recall, a week ago today, we had started the energy method, and what we had talked about is the internal energy due to strain. So if you apply a load to a member, that member is going to strain. That strain is like elongating a spring, and it's storing up energy. And then if you release the load, then the elastic member will return back to its original shape and the energy will be released just like a spring. But we talked about how that energy is, it's not force times distance, it's the average force times the distance. And then we went through and kind of made it more specific about the internal energy stored in an axially loaded member. So like a rod that's either being compressed or stretched. And we talked about the internal energy that is stored in a flexural member, where you have a beam, you put the beam in bending, you have compressive stresses in the top of the beam, you have tensile stresses in the bottom of the beam due to the bending. Okay, so we went through an example from beginning to end of a beam in bending, and we ended up doing the integrals, if you recall, and we had to integrate from, I forgot the points on the graph, but we had two parts to it, and then we summed it all up, and we found the deflection of a beam due to integrating the little m times the big M, all that, okay? What we're gonna do tonight to finish up this lecture is we also learned about the strain energy inherent in an axially loaded member, whether it's in tension or compression. So to find the deflection of a truss is simply the collection of axially loaded members. There's no shear, there's no bending in a truss. So every axial member of a truss can either be in compression or tension, but whatever that strain is, it all adds up to the total energy of the system. And so we're going to use this technique to find the deflection of a truss. Okay, so that's kind of just the 5-minute overview of where we were from the last lecture. Okay, so example number 2. We want to find the deflection at midspan using the virtual work of this truss. So pretty simple truss. I've got 3 loads on it, 2 40 kip loads and 1 20 kip load here. So it's not symmetrically loaded. And I have an area 1 for here, 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 and here. But the 2 inside diagonals are area 2. So they're not all the same area either. What we're looking for is the deflection at node C due to all the loading. Section properties, area 1 is given as 4 inches squared. Area 2 is given as 2 inches squared. This is a steel truss, so Young's modulus is 29,000 KSI. And what we want to do is if you recall, in fact, I keep saying if you recall, I don't even recall. So let me do this. Let's go back here just real quick. That's strain energy for bending moment. There we are. Okay, so strain energy for an axial load. And we got to this point here, where the internal energy of one axial loaded member is P squared L over 2AE. So that's the theory that we're going to use. And then let's skip ahead back to our truss. There we go. And here we are here. So what we're going to do is it's P squared, but I'm pretty sure what we're going to do is we're going to have little p from the virtual load times big P from the real load. So we need to solve the truss twice. We're going to solve it once for a virtual load of 1 kip, and we're going to solve it again for the 20, 40, and 40 kip loads, that is the real loading. And then we'll use that equation to solve for the deflection. Okay, so we want the deflection at node C. So the procedure is you put a 1 kip load in the direction that you want to find the deflection at the node that you want to find the deflection. So if you want to find the vertical deflection at C, you put a 1 kip load going down. If node C actually bounced up instead of down, then you would just get a negative result for your deflection. If you wanted to find horizontal deflection, say at D, then you put a 1 kip load going in the horizontal direction. Whatever deflection you're looking for, that's where you put the 1 kip load. So now what we need to do is solve our truss for a virtual load of 1 kip. So I'm going to solve for my reactions. I know this looks like a beam, but here's my reaction at A and my reaction at E. Well, I mislabeled that as B, but this is A and this is E. And solving for my reactions, I get a half a kip up at A, half a kip up at E, because the 1 kip was symmetrically loaded in the center. So then we use the method of joints to solve the truss. The slope members are all at an angle of a 3, 4, 5 triangle. So that helps with the geometry. And I start at joint A. And this is how you solve trusses, if you remember. You just start at one joint, you try to isolate it so that you have only 2 unknowns, and then you just progress your way through the truss solving. So I found my end reaction is half a kip. So I'm going to sum my forces in the vertical equal to 0. I have my positive half kip. My vertical component of AB is 3/5 of AB. So I have half kip up. Oh, and by the way, if you remember, always draw all of your unknowns as if they're in tension. Assume they're in tension, draw them in tension, and if you get a negative, like we do for AB, then that tells you it was actually in compression. So AB is minus 0.833 kips, negative, so that means this is actually in compression. Sum the forces in the X, and in the X direction, there's no load, but I have going to the left 4/5, which is 4/5, the horizontal component of minus 0.833 that we just found, plus AC pulling to the right equals 0. Therefore, AC equals 0.667 kips in tension. Now we can go to joint B. AB is in compression. I know that now, so I can go ahead and just draw it on the joint as compression. I take away the negative sign, it's just 0.833 kips in the correct direction. BD and BC are unknown, so I draw those in tension. Sum the forces equal to 0. And I have in the vertical, summing the forces in the Y. So 3/5 of 0.833 is up, minus 3/5 of BC is down, equals 0. So BC is equal to 0.833 kips in tension. I intentionally summed my forces in the vertical first because I only have one unknown with any component in the vertical. If I sum my forces in the horizontal first, I have 2 components in the horizontal, so I wouldn't be able to solve it directly. So kind of just keep an eye out for how you can isolate to one unknown as you're choosing how to sum these. Now that I have BC, now I can sum the forces in the horizontal. I have 4/5 of 0.833 kips to the right, plus 4/5 of 0.833 kips also to the right, plus BD. BD is then negative 1.33 kips in compression. Okay, any questions so far? Am I going too fast or too slow? No questions? Okay. Moving now to joint C. Joint C is where I have my 1 kip virtual load. I've already solved BC and I've already solved AC, so I put them on here as they are. Both of these ended up being in tension. So I have summing the forces in the vertical. Again, I'm trying to isolate the one unknown in the vertical direction, CD. So I have 3/5 of 0.833 kips tension, 3/5 of CD in assumed tension. AC has no vertical component, CE has no vertical component, but I do have a -1 kip here due to my virtual load. Therefore, CD is equal to 0.833 kips in tension as well. And of course, it would make sense that under the virtual loading, the truss is symmetrically loaded. So you should be seeing a mirror image of what you solved for on the first half. And that's what we get also. CE comes out to 0.667 kips in tension. I move up to joint D. And at joint D, you know what, I didn't put it on there, but I've already solved for BD. But I have minus 3/5 of 0.833. It's minus because it's negative, or it's going down, even though it's in tension. And DE is assumed in tension, but it's going down. So negative, negative. DE ends up being 0.833 kips in compression. And that does it. Here's my truss. For a 1 kip virtual load, my reactions are half a kip and half a kip because it was symmetrical. And you can see all the values for the individual struts or members that we had just found. Any questions about the first half, the virtual loading? Okay, now we do it all over again. We solve the truss for real loads. The real loads, if I treat this like a beam, I have 20 kips, 40 kips, and 40 kips. I solve for my reactions. I get 55 kips. This is actually E again, but 55 kips on the right-hand side and 45 kips up on the left-hand side. I use the method of joints to solve for the truss. Sloped angles is kind of just a repeat of what we just did, only now we have real reactions. So summing forces in the vertical, I got 45 plus 3/5 of AB equal to 0. AB is equal to minus 75 kips compression. Sum the forces in the horizontal, I have 4/5 of the 75 that I just found plus AC. AC is 60 kips tension. Joint B, don't forget to put the load on there. We have a 20 kip load at B. So the 75 that I know, the 20 kips of the applied load, and 2 unknowns BD and BC. So which one should I sum first, vertical or horizontal?
Vertical.
Vertical. Yes, I agree. Why would you do vertical?
We have only one unknown.
That is correct. I would do vertical because that way there's only one unknown and you can solve directly. So summing the forces in the vertical equal to 0. I have 3/5 of 75. It's pushing up, so it's positive. I have 3/5 of BC. It's pulling down, so it's negative. 20 kips is down. BC is 41.667 kips in tension. Now I can solve for the forces in the X. 4/5 of 75 to the right, plus 4/5 of 41.667 is also to the right, so positive, plus PD is positive to the right. BD therefore is minus 93.33 kips in compression. Joint C, I also have a 40 kip load at joint C, and I'm going to do the same thing. Sum the verticals first because there's only one unknown in the vertical direction. So I have 3/5 of 41.667 because it's pulling up, it's positive. 3/5 of CD, it's pulling up, so positive. Minus 40 equals 0. So CD equals 25 kips in tension, pulling up. Sum the forces in the X. I have minus 60. I have minus 4/5 of the 41. I have plus 4/5 of the 25 plus CE equal to 0. Therefore, CE equals 73.334 kips, and it's in tension as well. Joint D, again, I forgot to put in, we know what BD is here. So we can do the vertical of 25 is minus 3/5 of 25. It's pulling it down. Minus 3/5 of DE, it's also pulling it down, minus the 40 kips. So therefore DE is equal to minus 91.667 kips, and it's in compression. And here is my truss under the real loading. Okay, so everybody see that each one of these members has a value, a load assigned to it due to the virtual load, and another load assigned to it due to the real load. Okay, so now we can look at our strain energy. This is the equation we just found, well, last week, that the internal energy is P squared times L over 2AE. Conservation of energy, external has to equal internal. So the internal virtual work, if I apply a 1 kip load at the point of deflection and I solve, remember this was the virtual load times the real deflection is equal to the internal energy. So the delta 1 is real deflection, F2 is a virtual load of 1 kip, and so delta is equal to the integral from 0 to L of little n, big N over EA dx. Virtual load is applied before the real load, so the half factor is eliminated. Little n is the axial force due to the virtual 1 kip load as a function of x. Big N is the axial force due to the real load as a function of x. But in these truss type situations, little n and big N are going to be constant, which makes this a whole lot easier. Then we don't have to integrate it if the loads are constant over x. And so that's what we're going to do. We're going to, little n, big N, E, and A are all going to be constant for each member. So we're going to pull them out of the integral. And so what we do is we set up this table. And for each member of the truss, we have a length of that, which goes into 0 to L. It goes in the, up here, right there, it goes to L. We have an area assigned to it. Remember, the internals are 2 inches, all the other are 4. And we found our little n loads due to virtual loads. And make sure you get the positive and the negatives correct in this column. And also here too, we have the capital N due to the real loads. And so the individual internal energy of each member is going to be this little p or little n times capital N times L over AE. And that's what this is here. So little n, capital N, L over A. Actually, I pulled out the E, didn't I? So I'll put the E in back at the end. And so each one of these entries in the table is little n times capital N times L divided by A. That's what these numbers are here. And this is, oh, kip squared feet over inch squared. So this, I just straight across multiplied. Any questions so far? Everybody still with me?
Professor,
Yes, please.
how come they're constant?
Okay, good question. Okay, so in a truss, if I look at this member right here, and I measure X to be, say, from this left-hand end, no matter how far along this member I go, it's always going to be 75 kips of tension or compression, I'm sorry. See, so the force in this member is constant along the entire length of that member. There's nothing being applied that would change the load in the member as you're going along.
Okay, thank you.
Sure. So, and that's true for all the trust members, because as you notice, there's no loading applied on the members themselves. That's the definition of a true trust. The loads are always applied at the nodes. So all of these forces are all constant from one end to the other of each one of these members. Every member has a different load, but the load in the member is constant over the length of that member. Okay, so we're down here. So now if I sum the total of all this, which is really what we're doing here, the integral, we're summing all the pieces. If I sum all the pieces, I get 3,695.36 kip squared feet over inch squared. And so this whole integral sum here is the 3695.36. And then I convert it from feet to inches, and I divide by E, because remember I pulled the E out. And so 3695 times 12 divided by 29,000 KSI gives you 1.529 inches. And the deflection is down, or actually this is positive. So that means the deflection is in fact in the direction that you assumed it to be, which was down. Deflection is positive, so therefore is in the same direction as the 1 kip virtual load, down. If we had no clue which way the deflection was going to be, we could have put the 1 kip load going straight up, and we would have gotten exactly the same answer. It just would have been a negative answer, saying that we guessed the wrong direction. And that is it for energy. Any questions on the energy?
Sorry, can you pull that back up real quick?
I think I can. Let's see. I think it stopped the screen share. There we go. Can you see it?
Yes, thank you.
Okay. Any other questions on beam deflection or truss deflection?
I have a question, Professor.
Yes.
So just for clarification, the 1 kip virtual load is, you always put it in the point of deflection,
Yes.
because
Yes.
I thought you're gonna put 1 kip as well to the 40 kip and then the 20 kip as well.
No. So, and that's a great question. Thank you for asking that. The virtual load has nothing to do with the real load at all. So if you were to put more than one kip virtual load on the assembly at any time, you would get bogus results. They would not give you the right answer. So you can have multiple load cases where, let's get back, here we go. Okay, so say like this is the truss and this is the loading on the truss. And let's say you wanted to know, I want to know what the vertical deflection is at C. That's what we just did. But I also want to know what is the horizontal deflection at E. And there actually is one. If this was a pin and this is a roller, then as you bend this whole assembly down, it tends to pull in on E over here. So there is actually a horizontal deflection at E, even though there's no horizontal loading on the truss. But we can find that. All you need to do is, instead of a 1 kip deflection or a 1 kip virtual load at C, what you do is you put a 1 kip virtual load going horizontally at E. Again, nothing to do with the real loading. It's just an indicator of where you want to find the deflection. If, for example, I wanted to find the vertical deflection at B, then I do not put the 1 kip load at C. I only put it at B. So there's only ever one kip virtual load on the structure at any given analysis, but that one kip virtual load could be applied anywhere you want. And what it will give you is the deflection at that point in that direction.
Right. So let's say you said that there's a horizontal deflection. How would you find the reaction at A and the E in that case?
Well, reaction at A and E is going to be equal to 0.
Ah,
The reaction, again, assuming that A is a pin and E is a roller. So A can resist a load, but E cannot resist a load. There is no horizontal forces on the structure. E cannot sustain a horizontal force. So when you sum your horizontal forces at A sub x equals 0. There's nothing else there. So the horizontal reaction at A must equal 0. But that does not mean that the deflection in the horizontal direction at E is equal to 0. It's not equal to 0.
okay, that makes sense. Thank you.
Sure. If I go back to the beam problem that we did, this was last time. Okay, so on the beam problem, the problem stated I want the deflection at midspan. So I put the 1 kip virtual load at midspan. But we could just as easily, well, maybe it wasn't easy, but we could find the deflection anywhere on the beam simply by, instead of putting the 1 kip virtual load at midspan, we could put it wherever we wanted it. We could put it at the quarter point, the third point, wherever it is that we want to know what the deflection is, we could put that virtual load at that point, solve for the equations of moment for the virtual load, and then solve for the equations of moment for the real load, go through this procedure, and we would have the deflections due to the real load at that location. Any other questions on energy deflections? Okay, so we've got plenty of time, don't we? I didn't expect this lecture to take up the full amount of time, but whatever you would like to ask of me, now is the time. I don't think we're not gonna have this much time on Thursday, so really now's the time to ask about the final. But I felt that tonight would be the best night to really kind of go over the final, so that you have as much time as possible. You have a full week to study for it between now and next Tuesday. So please fire away. Who's got questions about the final?
What chapters will it be on?
For fear of sounding insensitive, it will cover all of them that we did homework on. So the final will cover, in the form of problems, the final will cover from chapter 1 all the way up to strain transformation, which I believe was chapter 9. And then like we said last time, the other chapters that we've done since then, where we did basically the energy method and the double integral method, and then the last lecture we're going to do on Thursday is going to be on column buckling. I could still ask you some questions from those topics, but it's not going to be a full-fledged problem that you have to work out.
How many questions will be on there?
I am planning on having 4 problem style questions. Yes, I did. We did homework. You know what? No, let me go back. Good question, Peter. Let me step back there a second. We did not do homework on strain transformation. We did homework on stress transformation. Okay, let me rephrase what I just said. The test will cover in problem form up to stress transformation. And then the topics of strain transformation and double integral and energy and buckling are open to question style questions, but not problems. Is that clear for everybody?
Yes. What about Moore circle? We have to do a problem on that.
Well, keep in mind that I can't tell you exactly what I'm going to put on there. So I'm not going to say yes or no to any specific thing, but Moore circle for stress transformation is open for the final. That's part of the stuff that we did do homework on. Even though I don't think I asked a specific question about Moore circle, but that was definitely in the chapter that we've had lots of time to look at. So it's fair game. Nicholas, no, it's not. It's not going to be mostly the stuff we learned after midterm 2. The final is comprehensive. So it's really going to be hitting what I thought was important. Some of it's going to be after midterm 2, but not all of it. Some is going to be the more important topics from before that.
For the non-problem style questions, how would that be structured and how many would there be estimated?
There might be some. And the way that they are structured is I'm just going to ask you a question. Like, because sometimes it's hard to make up questions. But it'd just be like a question like, E, capital E, stands for blank. And the answer would be Young's modulus of elasticity, something like that. Or it'd be Hooke's law states blank. And the correct answer would be sigma is equal to epsilon times Young's modulus. Stuff like that. Nothing's going to be true or false. Everything I do is true. But yeah, there's going to be some fill in the blank questions, and then you're going to have your 4 problem style problems.
Do you have any recommendation where to focus on the problems? Like, for example, the shear stress, that's for sure. And like this problem and whatnot.
No, you guys have listened to me ramble on now for 27 lectures, and I think you can get a gist of what is theoretical and what is important. What did I really spend a lot of time on? What did I really emphasize? What did I say that, well, yeah, you may see this once in your career, or, oh, we do this every day. So I'm not going to be one of those history teachers that looks for something really obscure from the 3rd week. It's all stuff that we've done plenty of work on now and talked about a lot. But really, my recommendation is to just focus on what I emphasized. But I don't want to lead anybody astray. I don't want to say, okay, everybody, we're going to be really important and do this, and then nobody studies something else, and boom, there it is. This is a comprehensive final. I don't want to sound, again, I don't want to sound insensitive, But this is a rigorous class. And to pass this class, you really have to have a fundamental understanding of mechanics of materials, because this class is the foundation of a lot of other engineering courses. I understand some of you guys, this might be your last class, but I'm teaching this class as a foundation for a career in engineering. Okay, so in the chat, okay, so you guys, you're gonna have to explain something to me, because I don't do social media. I know that's a shocker, but unless my wife tells me, go check Facebook because your daughter put something up there, and that's like maybe once or twice a year. Other than that, I have no clue about anything texting or anything. So having said that, what is the little upwards facing triangle? Okay, got to laugh out loud.
It's an arrow pointing upwards, so they're agreeing with what was said above them.
There, okay.
They're
Yeah,
like
so-
repeating that.
Yeah, everyone was
Pretty
just
much.
agreeing with the put the E question on the test.
Yeah. Put the what is E
Oh,
question on the test, like boost our confidence. Give us
Gotcha.
an easy one.
There'll be some easy ones. I'm not going to give you that. That's too obvious, but there'll be some. Yeah, you'll know them. Okay.
Have you written the problem style questions yet?
Sort of, kind of. So what I have to do this year, what you're going to see when, oh, okay, let me back up a little bit. First of all, I'm going to set up another Zoom meeting. I haven't done it yet, so that's why you haven't seen it yet, but I'm going to set up another Zoom meeting for the final. So everybody's going to log in and join the Zoom meeting for the final. And then what I'm going to do is, once everybody's logged in, I'm going to either verbally state it and or write into the chat. I'm going to put some passcodes. And you're going to use the passcode that is going to pertain to, I'll give instructions. I haven't really fully worked this thing out yet, but there's going to be more than one version of the final. So to answer your question, yes, I basically have written the final, but I haven't written all the variations of the final. There are going to be multiple versions. And the reason for this is that I'm not going to be able to mandate that everybody has a webcam so that I can see that everybody is doing what they're supposed to be doing. Again, this has been very, very challenging due to COVID in this virtual environment. If this class was like any other class that I've been teaching for 15 years, this would not be an issue because I would be in the classroom maintaining test security. But we can't do the Respondus lockdown anymore. And apparently I can't do a webcam as a mandatory feature of the test. So in order to come up with test security, what I was told was basically the only way that we can do a test security is to have multiple versions of the test. So that's what you're going to see. You're going to see multiple versions of the test, and I'm going to come up with some way, maybe first name, last name, I'm not sure yet, but there's going to be a way that you're going to see which version of the test, okay, which version of the test is your test, and then you're going to use that passcode to get to your version of your test. Everything else is going to be the same. If you want to put on your webcam, feel free. If you want the audio there, that's to your benefit so that you can ask me questions. I'll be there the whole time. So you can ask me questions with your audio. and that I don't understand problem number 3. Well, what's this number? Whatever, and I'll be there to assist. But yeah, that's how we're gonna have to do it.
Professor, so are you going to be switching through like, are you going to break us out like groups into like breakout rooms, or are we all going to be still in the same like session?
Yes, no, I gotcha. I don't really see the benefit, nor I'm not going to be able to figure that out in the next 5 days. So no, I'm not going to attempt breakout rooms. Everybody's going to be on the same Zoom, and it is totally voluntary if you want to have a webcam. It is totally voluntary if you want to have audio. That is totally up to you. Again, if you want to ask me questions, you can either chat or private chat or ask me a question, however you are comfortable. If you don't want to participate in Zoom at all, then what I would suggest is just tune in, get your passcode to get to which test you're supposed to be taking, and then once you're in the test, you can log off the Zoom if you like. The tests will still be timed, just like the midterms were, and basically everything else applies. How you turn in your work is exactly the same as the other two. The rules that I'm expecting everybody to follow for test security: no cell phones, no external help, no Googling answers, anything like that, is what I am expecting. But I'm not going to watch you. So
the test time frame is from 5 to 7?
the test is very close, very close. The test is from 5 to 6:50.
Okay, and then we have until what time to upload our documents?
Just like before, what I stated was within a reasonable amount of time. In my mind, that's 15, 20 minutes max.
Okay.
In the first and second midterms, that wasn't an issue. So I'm just hoping that nobody makes it an issue. Anybody else?
So for the lecture on Thursday, that's
Yes.
gonna be in our concept question as well, right?
It
For the
may
finals?
or may not be, but it could be.
Okay.
And you know why I'm doing that. Just get somebody to show up on Thursday. I mean, because I'm sure you're all interested in column buckling. I mean, it is, I'm fascinated by it, but I know also I did a lot of school, and I know that if I could have an extra hour and a half to study, I might be tempted to do that. So it's just my trickery to get you to tune in to the last lecture.
Is there going to be buckling on the final?
That's what I was just saying. There may be.
Okay.
Do you recommend studying all the exams? Is it gonna be something question like that? Like the previous exams?
Well, yes, but that is not to say that due to time or resources, that's not to say that if it wasn't on the first midterm, then it's not going to be on the final from the first third of the class. And that's not true. And that's not to say that if I didn't put it on the second midterm, then it wasn't important. So don't worry about it on the final. That's not true either. So I don't want to give you a false sense that the only things on the final are going to be things that I put on the first or second midterm, or that you learned since the second midterm. That's not true. But it wouldn't hurt to go back and review the first and second midterm, because generally what I put on the first and second midterms are what were important at the time. And so you see how this is it was a loaded question, kind of. But I do recommend you going back and reviewing the first and second midterm. And if there were some real structural, fundamental concepts that you didn't get, and then we went over the first or second midterm, we went over it afterwards, and you went, oh, no, I never heard that. I didn't get that. Okay, now I get it. Well, if there were some aha moments like that, I would definitely go back and review that, because really, again, the final is my best attempt to be sure that anybody and everybody who graduates or passes this class has a secure fundamental understanding of mechanics and materials. That is the utmost importance. This is the foundation to a lot of other engineering courses. And you can agree with me. You don't want people moving on if they just don't get the basic stuff in this course. I don't know how else to say it. It's almost like if you needed somebody to remove your appendix, would you want that doctor to be somebody who barely made it out of one of the foundational courses? You know, this is what an infection is. Oh, well, I kind of didn't get that, but okay. You know what I'm saying? This is a very important course to engineering careers. That would make sense?
Yes, thank you.
Feel like I rambled there a little bit, but I can, I mean, unless anybody else has a question they would like to ask me at this time, I can give you a little bit of my standardized advice.
I want to hear the advice.
Okay. I know I've said this before, but it doesn't hurt to say it again. When taking this exam, the first thing that I advise is look over, it only takes a minute, look over all the problems. Have in your mind what I'm asking of you for the entirety of the test. And you say, oh, problem 1 is this, problem 2 is one of those, problem 3, yeah, okay. And problem number 4, oh, yeah, I know problem number 4, that's slam dunk. So you know what to expect. And then manage your time. I've said this a billion times, but manage your time. And that is as important as knowing where to find stuff in the book, is managing your time. If you have 2 problems that you're like, oh no, he asked that, darn it. And there's 2 problems like, oh, okay. Yeah, that was a piece of cake. So manage your time accordingly. I would, maybe your strategy is to attack the ones that you are confident in, get them out of the way. Then you know how much time you have left over to attack the ones that you're not so confident in. However you manage your time, totally up to you, but do it. Manage your time. Keep your eye on the clock. Know how much time you have spent on each one of the problems. And by all means, and I say this every time, but somebody ends up doing it, do not spend the majority of your time on the one problem and then barely even touch 3 other problems. You won't pass the course doing that. You just can't get enough points doing it that way. It is much better to spend 75% of the time you wish you had on all 4 problems than 100% of the time that you think you have on 1 problem and 10% on the other 3. Mustafa has asked, do I have enough time to comfortably solve, or will we have to rush? If you really know the material, there is plenty of time. If you are confident in a couple of them, but not so confident in the others, and you have to look things up and kind of refresh your memory, there's still enough time. But keep in mind that I wrote this test so that there will be a time pressure. There's always going to be a time pressure, so that's one of the mechanisms that we can keep test security. If you had, well, I don't need to get into that, but that's one of the mechanisms for test security, is that you're not going to have tons of extra time to go and do whatever you want. But you will have enough time to complete this if you're properly prepared.
Professor, I have a question.
Yes, of course.
So for our cheat sheet, since we have double the amount of stuff to study for, can we get
No,
a
you
front
don't.
back page?
You only have 33% more.
Okay,
It-
so a page and a third then?
I don't care. You can take exam 1 on 1 page. You can take exam 2 on the 2nd page and fill in the margins or whatever. I don't care if you give me 2 pages, 1 page front or back, or 2 pages front. I'm okay with that.
Okay, thank you.
Again, as long as it's not worked out problems or whatever. It's just as we talked about. Okay, so let's see, I was on my soapbox, wasn't I? That was advice number 1, was managing your time. And that by far is the most important thing that you can do, is manage your time. You're not going to have tons of time to just dawdle and recheck and regroup and reread. You're not going to have that, but you are going to have enough time. If you're competent in the material, you'll have enough time to complete it. Number two is read the problem. And I mean, really stop the panic, settle yourself, read the problem, and read what did I give you, and read what am I asking of you. And I've said this 100 times as well, but I'm still getting, on the first midterm and on the second midterm, I still got some folks doing a lot more work than what I actually asked for, which is fine. It's just, I ignore all the work that's been done that didn't actually answer the question I asked for. I have to ignore that. That doesn't help you, it doesn't help me. I just go through and find the work and the answer to what I actually asked. So do not look at the problem and say, oh, this is a truss problem. Find deflections by energy. Okay, yeah. He just did that. All right. And you go through every single step that I just did, when I'm not asking for that. So my advice is read the problem calmly and carefully and make a note. I mean, I would write it down right there on the page. What did I give you? And very specifically, what am I asking you to give me? And just work to solve that. Don't do everything that the textbook does for this type of problem. Just do the work that you need to do to show me that you've worked through and came up with the right answer. Okay, so that's number 2, is read what I'm asking and answer, and only answer what I'm asking you for. But the flip side of the coin, maybe call this number 3. make sure you have answered everything I'm asking for. Make sure of that. Remember the second midterm. Remember that we had an actually loaded member. It had some loads on it, and then it had a temperature change on it. Do you know that most people lost points on that problem? Because I asked you to go through and tell me the stress, and then tell me the reactions, and then tell me the movement of a node due to the loading. And then the last part of it was tell me the movement of the node due to temperature change and loading. Most people did not add the temperature change to the answer they just got above that, which was the movement due to the loading. Some folks caught that. Most people did not catch that I was asking for the two to be combined. And that's why I'm saying, read the question carefully. Any questions on that? Okay. Does anybody else have any questions they'd like me to answer for the final? What to expect on the final? Okay, everybody's happy? Everybody's confident?
You still have one more office hours on Thursday, right?
Yes, sir, I do.
Okay.
Yes, I'll be here at 4:30 to 5:15 on Thursday. Yep. Anybody else? All right. Hearing silence, let's go ahead and call it a night.
Thank you, Professor. I'll see you on Thursday.
All right. Thank you. We'll see you on Thursday.
Thank you. Have a good night.
Thursday.
Professor,